huh? Hello? Hello. Good afternoon, everybody. So my name is Kim Saruji. I'm a scientist at the Gardner Center in UC Neurology, and I do basic research in Parkinson's. And I'll tell you a little bit about the new advances in Parkinson's basic research later on. But first, I have the pleasure of introducing someone to many of you who needs no introduction, Dr. Alberto Espay from the UC Gardner Center. And he will talk about this really excellent new biomarker program that's being initiated. Alberto?
All right, thanks Kim, and thanks everyone again for coming. This year is particularly special to us, not because of the new building that we have, but because it's a completely new beginning. In many ways, it's the beginning that we perhaps should have had earlier. And I'm talking about the beginning of a complete overhaul in thinking about aging of the brain, particularly as it applies to that thing we call Parkinson's disease. And the reason it's relevant is because we have a variety of treatments that are important for the symptom control of patients, but we've been trying to come up with strategies that deal with these symptoms at the core, not just how is it that we can prop up the dopamine system to be able to control symptoms, but how can we go above that level and start controlling the biology that goes awry and ends up causing the deficiency of dopamine that is so common. So we have all these many therapies that have failed, and a number in the pipelines, two of which on the right have about to be declared futile. So we have nothing to show for the concept that Parkinson's can be cured. And what I want to propose to you, and what the field is now finally moving into, is that we, as a set of biological rules that govern our brain, aren't that different from the rules that govern other systems. So when we think of Parkinson's disease, we think of this overall distribution. This is a normal bell curve, and essentially we say that there are individuals that are at both the benign end of the spectrum. They seem to have, or in this case, the malignant end of the spectrum, rapid accrual of disability, dementia that occurs earlier, and issues such as cognitive and autonomic dysfunction. And then individuals, we know, that could actually be in the other end of the spectrum, right? And we've seen that there is quite a bit of variability. Now, we always say that all of these individuals have Parkinson's disease because when we looked at their brains, they have something called Lewy bodies, and because we've seen so many patients who at the end of life, if we were to examine their brains, have Lewy bodies, they must all have the same disease. Now, let us review how we come to that particular conclusion. Let us remember that there is a fire in so many ways, and this is an analogy. You can think of it as a crime scene that happens. Let's think about the crime. When is the crime happening, and when is it that the crime scene comes to us as a way to determine what is it that we are dealing with? And what we really do is essentially something that perhaps may be akin to forensic research. We are examining the ashes of a fire and making conclusions. So when we do that, we are very much like this individual scavenging for clues and then finding that one thing that allows us to make two conclusions. Number one is, we were right. That individual who we said had Parkinson's, because what we're finding is exactly the evidence that tells us we were right. It doesn't matter that it was in one end of the spectrum or another. It doesn't matter what it looked like. We might have said, well, we think it's Parkinson's. We're not sure. But now we know it was Parkinson's because we have the confirmation that's what it was. Conclusion number 2 is the most damning. We have found the arsonist. This stuff must have been present at the very outset of the fire. In fact, before the fire ever got going, and it caused it. It is the crime perpetrator, right? So in that vein, the way we've been looking at biomarkers is a simple one. Since we know the truth, and that truth is defined by a constellation of symptoms that collectively we can call them Parkinson's, we can then define Parkinson's. And then, in fact, we're so good that we can define types of Parkinson's. We can define individuals who have tremor and individuals who don't. And we call them tremor dominant and PIGD, or postural instability gait disorder phenotype, because it makes us feel like we're really that sophisticated. We can tease Parkinson's apart into these 2 large types. And that's our truth. And so on that truth, then we measure biological signals that we can measure, and then apply statistical question. And that question is, of all the stuff that we're measuring, which ones correlate with one group that do not with the other? And if they do correlate with one group, we then say, we have found a biomarker. And that approach assumes that biology is to be measured to confirm that which we already know to be the truth. So how are we doing with that? Well, one example of many. So these are 2 different biomarker cohorts. On the left is the PPMI, or Parkinson's Progression Markers Initiative. We are part of it. That's to be said on the interest of full disclosure. On the right is the NOPA, de novo Parkinson's, a similar design. People who have Parkinson's are put together into a big bucket, and people without Parkinson's in another. And so the people are in the control group are called normals, and they create a normative mean that's dashed line horizontally on both. And what we measure, because we think it's very relevant, is the proteins that aggregate in the brain. Alpha-synuclein on the left is what makes Lewy bodies. But there are others, T-tau, P-tau, phosphorylated tau, total tau, A-beta-42. It doesn't matter to remember this, but it's important to emphasize that what we're measuring is what we think is very relevant. The proteins that we think aggregate and that we can find at the crime scene. So what you see is that in the one study, if we look at the correlations and what separates the patients from the normal mean, we find that there are 3 signals, the first 3, statistically significant below the normal of the mean, of the controls. The mean of the normals, I should say. But if you do the same analysis in this other cohort, you find that only one pans out, the others don't, right? So you're finding there is a discrepancy in terms of what you're finding, let alone that if you look at this data, you cannot conceive a future in which we might use it to make sense of a patient in front of us. It just isn't good enough because it's a lot of noise, and it is a statistical correlation. It tells us what's common across a large group of people, but not what makes them unique, not what's divergent. So where's Cincinnati? So for 3 years, close to 4 in fact now, we recognize that if we are going to make progress, we cannot, on one level, continue to assume that Parkinson's is many diseases, because we see it, because you guys know it. None of you can see somebody else that looks like you, right? We know it. So if you can admit, and we can as experts, that Parkinson's is not one but many diseases, let's be consistent. Let's walk the talk and not pretend that we are going to find a biomarker that will be significant across them all, or a therapy that will work for everyone. Otherwise, we're living a cognitive dissonance. We cannot both say that Parkinson's is many diseases, but that we are about to find a treatment that cured it all. No other field of medicine has ever done that. And neurology and psychiatry remains the last bastions of medicine, practicing 19th century medicine. So what we're doing then is collecting a large aging cohort. We just began, and this is an exciting project. I hope that most of you will be interested, both those of you who we all have something related to Parkinson's, but in fact, people who don't have Parkinson's, because we're looking for controls as well. We're reverting the order of development. We're not saying, here's a group of people that have tremor, what is it about them? Or here's a group of people with cognitive impairment, what is it about them? Rather, we're saying, here are the signals that are relevant, particularly signals that are key because it tells us about a mechanism of biology about which we already have a treatment, perhaps among the tombstones that we have declared futile. We're going to look correlations backwards from the signals to the individuals to create the first molecular subtypes of Parkinson's, Alzheimer's, and all other diseases of brain aging. We can have a success if we defined the biology of each of us. What will work for individual in the group of the D1, disease 1, molecularly speaking, will not work, or it might even be toxic for those who are in a different subgroup, explaining, of course, that we have failure after failure after failure in every trial ever done for Parkinson's and Alzheimer's. So this is essentially the idea behind the Cincinnati Cohort Biomarker Program, CCBP. We are planning on a 5,000 subject recruitment, 4,000 of whom will have a disease of brain aging. Some, and probably most by virtue of the type of clinic we have, will have something in the spectrum of Parkinson's, but there will be others with Alzheimer's, with frontotemporal dementia, corticobasal syndrome, PSP, etc. About 1,000 will be controls. It is a study like never before done because it assumes we don't know what we mean by Parkinson's disease, a concept that has served us well for symptomatic therapies, but it is irrelevant for disease modification strategies. We are now just about done with the recruitment of our cohort, of our internal cohort. These are the team of individuals that will be collecting all that data. We aim very soon to have about 18 patients per month. So we will really be interested in as many of you as possible to be able to meet our 5-year deadline of having enough of the power to find the small subgroups one at a time that will be suitable for therapies that we know have value for repurposing them into individuals that are molecularly suitable. I'm proud to report we have a great team of people entirely devoted to this project. They are shown here. They are all very keen. They have all already worked extensively. As I've mentioned, this has been years in the making. We are finally on the ground floor of an edifice that will be incredibly meaningful to all of us. Our goal is that within the decade, before the 2020s come to a close, we would have the first treatment for Parkinson's that will be a cure. Even if it's 1 or 2% or 3% of individuals, we want to have a success on which to build upon further successes. So that the future, therefore, is one where we begin to tease out what is it about each of us that makes us unique, not only behaviorally, but molecularly, such that then we can define what is it that we need to target and who we need to target. The warfare against Parkinson's disease can only be won if we're smart. If we recognize that the greatest question about Parkinson's is to answer the who. What makes us unique? And we will do that. Before the 2020s are over, we will have the first treatment that will slow down or disease progression of Parkinson's. Thanks, everyone.